slide showing window. Great. I just want to make sure you guys can see my slides nice and big. Should say graph neural networks on it.
Yeah, we can see that.
Yeah, it's clearly visible.
Okay, good. That's usually my problem. I never get it clearly visible. Okay, great. Okay, so what's the story with today's workshop? We're going to talk about how graphs represent data and how we might represent graphs and what kind of machine learning we can do with these graphs. Then we're going to sort of like go back to convolutional neural networks and talk about going from convolutional neural networks to graph neural networks, then talk about graph convolutions with code. And then we're going to do multiple graph convolution layers and this kind of idea of receptive field that you might be familiar with from convolutional neural networks. And come up with a paradigm in which we can train graph neural networks called the message passing paradigm. We'll have a baseline model with code because after all, if you're doing any kind of machine learning problem, you should have a baseline problem. Then you should, let me make that a little bit bigger. I guess that's okay. Then we're going to talk about graph convolutional model for doing node classification in a graph. And then we're going to talk about some other models and we'll talk about tasks, graph tasks that we can talk about. The first question you might actually ask is why on earth should you care, right? About graph neural networks. What's so interesting about them? Why should you, why bother? Why bother with learning about that? And the answer to that question is along the lines of, we should stay here. Well, just about everything that is not an image or language, even language actually is, and even an image actually is, just about everything else is a graph. So your social network, well, that's a graph. You want to find the structure of a molecule, well, that's a graph. You want to find the structure of how disease, propagates in a population, well, that's a graph. You want to look at a citation network of links and so on and so forth, that's a graph. You want to see a bunch of web pages, well, that's a graph. You're looking at a semi-structured document, right, in which you have, like a paper, for example, in which you have sections, and you have concepts and sections, well, that's a graph. You want to look at a contract which is happening between two companies, well, that's a graph. You want to look at a legal document, well, that's a graph, with different sort of like parties involved and different contractual parts, different parts of the law, different sub-laws and bylaws which are being referred to. So anything which has this kind of, relationship-like structure, essentially, is a graph. And so if you want to model anything with relationships, anything more complicated than a simple table or an image, or I won't say language is simple, but or more complicated than language, you are going to need a graph. And the whole idea of neural networks is basically you are going to model stuff using a complicated nonlinear function. And why not do the same thing for graphs is sort of like the point right over here. So that's sort of like the reason why I think you should care about doing graphs. There are other reasons to care, like protein folding. All of these things can be modeled as graph neural networks. There was a recent paper that came out which modeled both Newton's laws of physics as a graph, but also modeled essentially came up with a method to derive Newton's laws from observations of a pendulum, basically. Derive Newton's laws from there, but not just derive Newton's laws in an empirical form, right? If I wanted to sort of like make sure that the pendulum actually works, I would put in a differential equation or something with Newton's laws into the equation and then actually try and make sure it fits. But this one not only derives Newton's laws from it, but actually derives the functional form of Newton's laws. So it actually represents the equation of Newton's laws as a graph and then derives a graph structure. So equations are also graphs. So you could actually derive symbolic physics using graphs. There's all kinds of crazy applications that people have come up with for graphs and therefore for graph neural networks. So for this talk, I'm actually going to be extremely basic, and the problem we're going to solve is one of a citation graph. And a citation graph is like, you wrote a paper, and in that paper, you cited Sheetal's paper, and Sheetal's paper cited Bhaskar's paper, and Bhaskar's paper cited my paper, and so on and so forth. So you have the citation graph going. And what we want to do is we want to predict what is the class of a particular paper given its citation graph. Now, a simple idea you might have to predict the class of a paper. Well, is this a machine learning paper? Is this a computer science paper? Is this a neural networks paper? Would be, okay, well, let's just look at the terms inside there, right? The words inside of that, and then create a word model, for make all the different words features and train a model using that. And that should do pretty decently. And the truth is it will do pretty decently. But if you want to get that little bit of extra juice into this problem, right? You want to go from like 70% accuracy to 80% accuracy, or 70 to 75% accuracy. What's the simplest thing you could do? You can basically say, well, okay, Bhaskar works in machine learning. Rahul works in machine learning. So if Rahul cited Bhaskar, there is a greater likelihood that Rahul's paper is a machine learning paper. So that's sort of the notion. And that additional piece of information is what I want to bring into this problem to try and make my classification better. This is, of course, not the only classification problem that you could think of. You could actually think of classifying an entire graph. So for example, you have a molecule, and you want to classify a set of molecules as either poisonous or not poisonous. Do they have a particular structure which make them poisonous? Okay, well, you can ask that question, right? And falsify your hypothesis that all poisonous molecules share a particular structure. So that's another example of thinking about it. But that's a different kind of model, right? You're asking the question, what's this whole graph? What kind of a beast is this graph? Another idea you might have is to actually predict links, not predict the graph, the people in the graph, but predict the kind of link. Like what kind of citation is it? What kind of link is it? Is it a spammy link? Is it a link just to do spam? Is it a link not to do spam? The class of the link on a set of web pages you might want to predict. Other thing you might want to predict is, should there be a link between two things? These things, I don't know whether there is a link between them or not. In fact, if you think about the training data and the test data, for the test data, I would just hide the links from you and tell you, okay, well, predict if there's a link between these two papers, or predict if there is a link between these two web pages, or predict if there is a link between these two people. That's another sort of problem I want to solve. So these are, the different kinds of problems you might want to solve with graphs. And for today's talk, I have liberally stolen images and equations from the following sources. And I've linked all these sources for you in the PDF as well. And they're all extremely good sources, which I strongly recommend reading. And I actually strongly recommend reading them, roughly speaking, in the order in which it's in this page. And my feeling is that it'll become very easy for you to read these after today's workshop. So I would not consider this workshop as a one-off. I think you need to go a little bit deeper. This is a big field. And in a sense, this is my kind of like introduction to the field for you. Okay. So graphs. What are graphs? Well, I mean, they're things connected to each other, right? So when you say things connected to each other, you need a word for the things. The things are usually called nodes or vertices. Thing. And then there are connections between the things called edges. Edge. Sometimes the edges have directions to them. Rahul loves someone. Rahul loves someone else. Oh, we have trouble. And we have like a triangle over here because someone else loves someone else over there. So, okay, good Bridgerton style, soap opera type situation going on out here. Okay, well, you could have an undirected graph, right? An undirected graph is that nobody loves anybody, but there's some relationship between these two out here that we're talking about. So that's another possibility. We might want to label these edges. This person's kind of lukewarm about this other person. Another person, if it's a 2 or a 3, is a little bit more hot about that other person. So that's sort of like an edge label kind of graph. You might have a node label graph, right? Yes, and the node may be like, this is a karate club, and this is how good the person is at karate, for example. So you're essentially qualifying the person. It may not just be one number, right? It may be a huge number of numbers: height, weight, black belt, blah blah blah, all of these kind of things. You may want to attach all that, an entire row of a table of information to that node if you wanted to. And then you could combine these two, and you might have both labels on edges as well as nodes, right? So these are the different possibilities of the kind of graphs you might actually encounter. So the sort of like basic idea is I have some nodes, I have some attachments, and the nodes as well as the edges, in this diagram, it's only the nodes, have some kind of feature vector associated with it, which I'm here calling x1, here is x2, here it's x3, x4, x5, x6. There's 6 different feature vectors here. Normally, if you were to look at this in a table, right, it would be like x1, x2, x3, x4, x5, x6. I have this table. But there is this additional piece of information that there is some kind of connectivity between them. Like 1 is not directly connected to 5, but 1 is connected to 6, 4, and 2. There is this connectivity information, which is not really there in this table over there. So Ashwin is saying, I joined late. Will the presentation be shared with us? It already is. There is a link. Let me see if I can copy and paste it. Oh, okay. Shivani already did. And you can get the presentation from inside there. And there's a collab notebook as well. Okay. So let's talk about representing this graph. Very, very simple ideas of representing this graph. This is a four element graph, and we have some colors on the nodes. And let's say these colors are our features, right? And we have how many colors? We have 3 colors, right? So simple idea, one hot encode the colors, right? There's green, blue, orange. And so, the node number 1 is a blue node. So you get 0, 1, and 0 up there. Node number 2 is the orange node out here. So you get 0, 0, 1 as a feature vector associated with that node. Node number 3 is another blue, so it has exactly the same 0, 1, 0 feature vector associated with it. And then node number 4 is 1, 0, 0 because the green is the first thing. This is the way we just listed it as green, blue, orange.